So having said that, time to move on to the next talk. So we have Madhavan, who will be teaching us about the same themes, and there's lots of interesting things to say, but I just wanted to say that I think I saw on the internet one of the cutest pictures of a research group, or by his group. Just go look online, there's really a very cute picture of absolutely, I think, the youngest research group, I might say. It's quite adorable. In any case, on to science. The floor is all yours.
Thank you. Hey, thanks a lot for the introduction and advertising my precocious research group. So first, I'd really like to thank the organizers for giving me this opportunity to speak about some new results. So what I'd like to do is to share some new results which pertain to the construction of dynamics for quantum gravity. And I'll work within the canonical quantization approach to quantum gravity, which is known as loop quantum gravity, and which you heard about in the first part of Hal's talk, which just preceded this one. So what I'll do is I'll begin with some introductory remarks, which will serve both to review the relevant background as well as to set a proper context for these new results. And so let me start with a review of how we understand dynamics in the classical Hamiltonian formulation of, say, vacuum gravity. So we have a space-time manifold M with a space-time metric little g. The Einstein equations are satisfied here. The space-time is topology sigma cross R. There is a there's a time evolution vector field on this space-time, and slices of constant time are all diffeomorphic to sigma. On each such slice, the space-time metric induces a spatial metric Q, and this Q serves as one half of the phase space variables. The other half is called P, and that encapsulates information about the extrinsic curvature of this slice as embedded in the ambient space-time. Dynamics along this vector field is generated by a Hamiltonian. So what the Hamiltonian does is that it evolves data from one slice to another, and that is what evolution is in the classical theory. One can then solve the Hamilton's equations, and then one gets a one-parameter family of these Q's and P's, one for each slice. And from this one-parameter family, one can then reconstruct the space-time metric, which then goes and satisfies the Einstein equations, and that closes the circle. It's useful to decompose the time flow vector field into components normal and tangential to the slice, and these are parameterized by the lapse and the shift. So the shift is tangential to the slice, little n is the normal to the slice, and the lapse is the amount which you go normal. The Hamiltonian then resolves into a sum of two generators, one which generates the evolution normal to the slice, and which is called the Hamiltonian constraint, and the other which is generating transformations tangential to the slice, and that is called the diffeomorphism constraint. And of course, it's so called because what it does is that it turns out to generate three-dimensional diffeomorphisms of this data. So the non-trivial evolution out of the slice is really governed by the Hamiltonian constraint. And so in the quantum theory, the corresponding Hamiltonian constraint operator is what controls the dynamics. And hence its construction lies at the very heart of canonical quantum gravity. This classical constraint is a very complicated function of the Q's and P's, and I think one briefly encountered it in Klaus's talk, maybe on Monday. And it's complicated both for Lorentzian and Euclidean gravity, and therefore it has resisted attempts at a rigorous quantization. I'm going to focus on the Euclidean constraint for reasons which are going to become clear shortly. Now, while the Euclidean constraint is a very complicated function of the Q's and the P's, it acquires a very simple form in the Ashtekar-Barbero variables, the real ones which Hal talked about. And the simplicity of form is what makes it then much more amenable to quantization efforts. So what are these variables? Let me review from Hal's talk. These variables are an SU2 Lie algebra valued electric field. So the index A is a tangent space index, and little I is a SU2 Lie algebra valued index. And there is a conjugate connection, which we call A. So since the Lie algebra of SU2 is three-dimensional, we have EA1, EA2, EA3. So there's a triplet of spatial vector fields, and these are interpreted as a spatial triad. And this then, from the spatial triad, you can then go and construct the metric. So the E's contain all the spatial metric data, and therefore the conjugate variable A has the extrinsic curvature information. So this is just as Hal also reviewed. The Hamiltonian constraint then takes a very, very simple form. So it's an integral over the spatial manifold. There's a factor of the lapse, and there is a polynomial term. So there are two E's and an F, where F is the SU2 curvature of this connection. And then you have a non-polynomial piece, which is 1 over square root of the determinant of the 3 metric. And remember, the 3 metric is constructed from the E's, so this is actually a function of the E's. And this non-polynomial part is there so as to render this integrand of density weight 1 so that you can integrate it without trouble over the spatial manifold. So our aim is to construct the corresponding quantum operator in the LQG representation which Hal introduced. Okay. Now, since in GR space-time is itself dynamical, there is no preferred background. All background objects are fictitious and unphysical, and the guiding philosophy of LQG is that it aims to construct everything, and in particular the Hamiltonian constraint operator, without relying on any fictitious fixed space-time background structures. And this kind of quantization or setting up quantum field theory in the absence of any space-time requires new ideas and techniques beyond those which have been developed so well for quantum field theory in a fixed and often flat space-time. So these ideas and techniques were developed by a huge number of people, I guess out of which Jurek Lewandowski was supposed to be here but is not, and Renata, she hasn't bunked my talk, is also somewhere around here. Here she is. Okay. And so all these efforts then culminated in Thomas Thiemann's construction of the Euclidean constraint operator in his quantum spin dynamics work. Thiemann also showed in that work that one could construct the constraint operator for the Lorentzian theory from the Euclidean constraint and the volume operator. And the volume operator we know is defined in LQG. This was a big theme of Hal's talk. And so the first step in this business is to actually focus on the Euclidean constraint operator, and then we can go and construct the Lorentzian one. And this is why I'm restricting in this talk my attention to the Euclidean Hamiltonian constraint operator. So the QSD construction of Thomas was of this Euclidean constraint operator was and is a spectacular achievement. However, some open problems do remain. There are many ambiguities in the final operator action, and I'll come to this soon. And secondly, the constraint commutator between a pair of Hamiltonian constraints does not reproduce the correct lapse dependence of the operator correspondent of its Poisson bracket. And from classic and beautiful work of Hodgman, Kukash, and Teitelbaum in the 70s, this particular dependence of the lapse turns out to be intimately connected with the implementation of space-time covariance in the quantum theory. So this is quite important. In our view, further progress on these two issues was handicapped by the absence of any intrinsically three-dimensional interpretation or intuition about what this classical evolution constituted. So just to remind you, for the diffeomorphism constraints, one exactly has such an interpretation. The diffeomorphism constraints just generate three-dimensional diffeomorphisms of this phase space data and capturing that intuition or that geometrical interpretation in quantum theory is really what allows one to represent in LQG the diffeomorphisms correctly as unitary operators. So the hope is that perhaps if one had a little bit more intuition about what the Hamiltonian constraint does in purely three-dimensional geometric terms, maybe we could feed that and imprint it onto our constructions in the quantum theory and thereby perhaps make progress on these two issues. So this brings me to the main take-home message of this talk, which is that classical gravitational evolution in time, which is generated by the Hamiltonian constraint, can now be reformulated or thought of in terms of certain spatial diffeomorphism-like transformations. This is a bit vague, but will become clear in the next slide. And these transformations are generated by a triple of shift vector fields. So these are spatial vector fields constructed from the electric field data. This classical insight dovetails naturally into a new construction of the Hamiltonian constraint operator for Euclidean gravity, in which these diffeomorphism-like transformations of quantum states associated with this electric field play a key role. And this new Hamiltonian constraint operator then has improved properties both with regard to the issue of ambiguities and space-time covariance. It doesn't offer a complete solution, but it does have improved properties. So let me now turn to an account of this new classical insight. And in order to do so, I'll just make a very brief digression on Lie derivatives and their gauge covariant counterparts or generalizations. So consider a Lie derivative of a Lie algebra valued vector field. So here again, the little I is the Lie algebra index with respect to an ordinary vector field V. So one can just write down the usual expression, and then one notices that under rotations, gauge rotations of this index I, this object is not gauge covariant. So if you want to make it gauge covariant, there's a simple way to do it. Given a connection, you can just replace the ordinary derivative by gauge covariant one, and then this of course is gauge covariant. And at least to my knowledge, this was first written down by Jacques, who also is no longer with us, way back in the early 70s, I think. And there is a nice geometrical interpretation of this object, and it really corresponds to infinitesimal translations along the horizontal lift of the integral curve of V to the principal fiber bundle. Now, what if this vector field V also was Lie algebra valued, that it had internal indices? Well, one can define just by analogy an object which we can call a generalized gauge covariant Lie derivative, and which is basically just, since this object has an internal index, now we just in both instances replace this by the gauge covariant derivative. So this also depends on the choice of a connection, and the exact geometrical interpretation of this, unlike the gauge covariant Lie derivative, this geometrical interpretation is still open. So while one doesn't have an exact geometrical interpretation, yet there is probably some very rough, vague intuition that this object has something to do with some sort of transformations which are associated with this Lie algebra valued vector field. And that's all I'm going to use to motivate what I'm going to do in quantum theory. So now let me, after this brief digression, go back to general relativity, and from the electric field data and the lapse, I can define up to some other factors which I'm not going to get into. I can define something which I call the electric shift. So this is a Lie algebra valued vector field because of this index I, and then it turns out that the evolution equations generated by the Hamiltonian constraint on the constraint surface take a really intriguing form, which is that the time derivatives of, say, the electric field and the curvature are just written directly in terms of combinations of these generalized gauge covariant Lie derivatives with respect to the electric shift of the fields themselves. So of course, this depends on the connection, and the connection is the second part of the data. So you have the electric shift, which depends on the electric field, and the connection creeps in from the definition of the generalized gauge covariant derivative. But nevertheless, this is really a beautiful and extremely intriguing form, and I just wanted to exhibit it over here. And therefore, the message for quantum theory is to try to encode the action of the Hamiltonian constraint operator now in terms of transformations which are generated by the electric shift, which now becomes an operator because it depends on the phase space variable, which now becomes an operator. So that is the aim of what I'd like to do. And let me then go on now to quantum theory and just quickly recap, maybe in a slightly complementary way, what Hal did. So let me very, very quickly in 2 slides tell you about the quantum kinematics of LQG. So it's a connection representation. Wave functions are functions of the connection. The basic connection dependent operators, as Hal pointed out, are holonomies along edges in the Cauchy slice. So if you give me an edge in the Cauchy slice, I can integrate the connection one form over the edge like this, and there is a path ordered exponential which you write down, which is gauge covariant, and in order to actually go and sum the series term by term in this exponential, you need to use some representation of SU2. So this also involves implicitly a spin representation of SU2, so j equal to half, 1, 3 by 2 or whatever. So the holonomy operator then just acts by multiplication. So you have wave function of the connection, and then this acts simply by multiplication over here. So you get a new function of the connection. And the triad operator acts by functional differentiation. And here you have the factor of g, which comes from the symplectic structure, which reminds you that you're in quantum gravity and not in Yang-Mills theory. States are linear combinations then of, you can go to a basis of states, and in this basis, states are linear combinations of products of these edge holonomies. So if you draw an edge holonomy over here, you also have to color it with the representation in which it's evaluated. So you have like a pink edge over here, which might be j equal to 5, and a purple edge with j equal to 3, etc. And so the collection of all these edges in the product form a graph, and therefore you have a colored graph over here. And if you take the action of the holonomy operator, and let's say that we construct, we're interested in the action of the holonomy operator when the edge is a loop, then what it does is that it multiplies the product, so it also comes and joins the product over here, and therefore this edge is added to the existing edges of the graph, and so you just add this edge over here. And you can see that the new graph then has some extra vertices, and then there is a place where the purple and the black edges overlap. So this over here is a multiplication of an edge holonomy in the black representation and the purple representation. Then you can use Clebsch-Gordon decomposition to just write this in terms of sum over angular momenta representations, and the end result then is a sum over these colored graphs, which are uniquely colored. So every edge has a unique color. So that's how the holonomy operator acts. The operator which is of interest for us is the volume operator, and that is constructed from the triad field. And it turns out, Hal hinted at this, and it turns out when you actually regulate it and then take the regulator away and write it down rigorously, the action of the volume operator on one of these colored graph states is only non-trivial at its vertices. So if you have a volume of a region R, and if that region intersects a vertex of this graph, or contains a vertex of this graph, then you get a non-trivial contribution. If there are no vertices in this region R, then the action is just trivial. It annihilates such states. So much for the kinematics. What about the evolution? Well, first the tangential evolution along the slice, which is a diffeomorphism. And it turns out, due to the background free quantization, that diffeomorphisms turn out to be unitarily implemented. And their action is very simple. What a diffeomorphism does on one of these colored graph states is that it just moves it along by the diffeomorphism, preserving the edge colors. So now let's go to the Hamiltonian constraint, which is the quantum dynamics normal to the slice. And recall that the Hamiltonian constraint for the Euclidean theory was just some polynomial part, and then there was a square root of q dependent factor. Recall also that the volume is built from this square root of determinant of q, and then it turns out that just like the volume operator, the square root of q operator also acts only at vertices of states. So with appropriate operator ordering, the Hamiltonian constraint action is then just a sum over vertex contributions, and at each vertex we then need the action of the curvature operator. And this actually presents us with the following absolutely key problem, and which underlies, this is really the heart of the problem which we face. The problem is that the curvature is the local function of the connection, whereas the basic connection operators are non-local holonomies. So classically, there's no problem. One can just extract coordinate components of the curvature from taking a small coordinate size delta loop, right? And then you can just verify. You take the holonomy -1 divided by the coordinate area of the loop, take the limit delta going to 0, and you'll get some suitable coordinate components of the curvature. So what do we do quantum mechanically? Quantum mechanically, one looks at the expression for the Hamiltonian constraint and replaces the operator by this regularized expression, and then tries to take the delta going to 0 limit of the Hamiltonian constraint, whatever the expression is. So the good news when we do this is that one can actually define this limit, take delta going to 0, and hence we can define a constraint operator. But the bad news is that this final operator action, unfortunately, depends on the choice of small loops, so what its shape is, how it interacts with the graph state it's acting upon, and it also depends on the representation or color of its holonomy. And this is really the problem of ambiguities, which will become even more clear on the next slide. So here, I home in on one of the vertices where the Hamiltonian constraint is going to act. And typically what happens is that the choice of loop is dictated by simplicity, and the representation of the loop is taken to be j equal to half. So skipping over some technicalities which are related to taking this delta going to 0 limit, an accurate pictorial representation of the essential features of this operator action with these choices is as follows. What happens is that the Hamiltonian constraint, because of the determinant of q factor, comes and homes in on the vertices, and then at each vertex one adds a loop which is a curvature approximant, and the simplest choice of this loop is to make it a triangular loop. So choose two of the pre-existing edges of the graph and construct two parts of the loop from them, and then close it with what is called an extraordinary edge, and then color it with j equal to half. So you can see that if j was not half, it was some purple, pink, blue color, right? Then you would get a different colored graph. And also if it wasn't triangular, but it went and it interacted in some way with the other edges of the graph, you would again get a different kind of result. So, and then of course you sum over all contributions with all pairs of edges, but nevertheless this is really the source of the ambiguities in the final operator action. So let's see now how we can alleviate this a little bit by moving on to these new results. So what is the new construction? So recall that in the classical theory we were asked to focus on the electric shift. So let's do this in the quantum theory as well and see what happens. So recall that the Euclidean constraint was just this n, e, e, f, and the square root of q dependent factor, and this n times e is already the electric shift, so it's sitting right there in the operator itself. And in quantum theory, this ne becomes an operator, the electric shift operator. Again, the square root of q dependent factor yields a sum over vertex contributions, and so we have the electric shift operator which acts at each vertex. Now the simplest objects, if you notice, this has a certain structure with a tangent vector index over here, and the simplest objects at a vertex with this sort of an index structure are just the edge tangents. So what happens in detail is that this operator pulls out factors of edge tangents, and when all the dust clears, the constraint action becomes naturally implemented in terms of diffeomorphism-like translations along the edges at the vertex. So supposing I fix a particular edge and call the diffeo-like translation along that edge by phi e, then this is roughly what happens pictorially. So phi is, we call an electric diffeomorphism because it came from the electric shift, and it turns out that the small loops which encode the curvature operator are now built from the action of this phi e on the remaining edges at the vertex. So let's fix the blue edge over here. We have this vertex. Let me fix this blue edge to be this edge E, and let's look at one of the remaining edges, say the brown edge. So what this guy does is that it pulls this edge up in a diffeo-like manner and creates this edge. And if you look at what the corresponding loop is, then it has exactly this segment over here, and then you go along the original edge, the original brown edge, and you close it going along this blue edge over here. And because it's a diffeomorphism-like transformation, it doesn't change the labeling of the brown edge, so the loop is in the brown representation. So what has happened is that the labeling ambiguity, whether it was j equal to half, 1, 2, is now gone. The labeling is just attuned to the particular edges of the graph, which are already existing, what their colors are, and then the shape of the small loop is really determined by the way these electric diffeomorphisms act. Okay, so that's what I've said again. The color ambiguity is fixed. The geometric understanding of shape is now there in terms of what these electric diffeomorphisms do. And one also gets the correct lapse behavior. In fact, in detail, one can show that on a suitable space of states that the commutator between two Hamiltonian constraints is anomaly free, so that you get exactly the operator correspondent of its Poisson bracket. And this was one of the ingredients for the emergence of space-time covariance from the canonical theory. So just to summarize, I'm almost done. This is sort of the technical part, and the new results are now over. I'll just summarize. There are still ambiguities which remain, but the Hamiltonian constraint operator action is certainly better determined. It beautifully implements our classical intuition, and in passing it seems closer to its detailed physically appropriate implementation in mini superspace quantization known as improved LQC, and in my view constitutes exciting progress. I started 5 minutes late, or 7 minutes late, so I will just flash a couple of slides and then stop. Because I was asked to also comment on problems for the future, at least as I see them in the canonical theory. So one is, of course, to now try and apply this new dynamics to mini and midi superspace contexts. There's another very interesting subject to probe, and this is the transition to Lorentzian theory, and this is due to an old idea of Thomas, where he constructed a complex canonical transformation which led you from the Euclidean self-dual variables to the Lorentzian ones, and he also suggested a way to implement this in quantum theory, and once you do that, you can actually take solutions to the Euclidean constraint, apply this operator, and rotate to solutions to the Lorentzian constraint. So this is a beautiful idea which I think deserves further study. Let me flash a few references over here, and then this was my final slide, and I can either go through with it or I'm done, and you can read it as you wish.
We have time for one question. How about that?
Sorry?
Let's go for people reading it, and then we
sure.
have time for questions.
Sure.
Thank you very much. So, anyone? Yes, we have one up there. Okay, on my way.
What do you mean by the action of this commutator is represented on a suitable set of states? What do you mean by suitable in terms of spin nets or group averaged?
There are certain distributional sums of spin network states, right? So which they have to be off-shell, so they can't satisfy the constraints, otherwise you'll just get 0 equal to 0. So there's some off-shell distributions which one can construct, and on this large set of states, one can show that this constraint algebra is satisfied. So the actual definition is quite technical, so but it's basically some set of off-shell distributional states.
To not cut too much to the coffee break, I'm sorry. If you have any extra questions, okay, fine, one, and then coffee break. I hope it's brief.
Okay, the question is, you took this point of view of adding a little loop instead of adding a bigger loop, and it's just a bigger loop as if you had a triangulation of given by the spin network or something, and then adding a bigger thing that doesn't change the graph. Just I asked this thing as a route to connect it to spin-form models and the deformation algebra there. Do you have any comment on that?
Yeah, so this is, okay, probably the question is short, but the answer may be a little long. You can cut me off. This really has to do with understanding the physical state space. And there is, so contrary to sort of what people thought, right, the physical state space, in order to actually get non-trivial solutions, is an extremely complicated affair, right? And when you actually solve physical states, these are linear combinations of these spin network states, right? And in this, so you will certainly have things where you add these small loops, but you also have objects which somehow which have to be there, which are more analogous to having these larger loops, right? And I can tell you more about this in detail. This is related to this propagation work which I did with Thomas. So there is room, actually, I think, for at least some amount of contact with this, but maybe not in exactly the way you want, but we can talk about it more.
Great, indeed. Let's continue the conversations over the coffee break. One big thank you again.